All right, so here we go with the end of the course. We're going to go fast and kind of furious a little bit. Hopefully I can awaken the gods in terms of electrochemistry. Okay, so let's get started. We're going to start with the first application of redox, okay, which is the Voltaic Cell. All right, we're going to mark this up. Now, in the packet that I gave you, okay, I wanted to show you what it would look like as a part 2 question and how I broke it up. So I broke up this question so that we can write in it. Okay, but if you look at the next page, you can see how the question is presented. So it's the same question, I just separated for us to be able to work in it. So like when you get a question, never put your answer in the booklet's question. Like there's not enough room. It's not made for it. It's made for a booklet. But I did this purposely so we can work together. Okay, first and foremost, these questions, although they may be redox, maybe acid-base, they're always going to have a tinge of something else in there. So here's a great example. Even though this question winds up being a redox reaction, a Voltaic cell reaction, it starts off with something that's not redox. It's basically what? Atomic structure. So write the complete electron configuration of zinc plus 2. So they're asking for you to write the configuration of this ion. So we know zinc, okay, is all the way over, and you would use your reference table, it's right here, okay? So we know we're going to end up in the 4th energy level, but we're in the D block, and this D block belongs to the 3, so this is 3D10, okay? So I don't know how much you remember, but if I go in order, okay, of course it says complete, so you can't use, in this case, the what? The shorthand method. All right, I would go, and let's go blue if you think this makes you feel blue, 1s2, that's hydrogen helium, 2s2, 2p6, all right, 3s2, 3p6, and for those that don't know where I am, I'm in room 230, but I went 1s2, 2s2, 2p6, hey, 3s2, back in the S block, 3p6, argon, okay, 4s2, and now this is 3d10, and that would be for zinc, but they asked for what? Zinc plus 2. Well, let's go to zinc. 3p6, 4s2, 3d10. That would be for zinc, and if we wrote this, it would be wrong. But when we did this months ago, what did we learn? The transitional elements, or elements in this area, are going to lose their what first? Their S first. That's why most of them become plus 2. And why? Because the 3d10 will what? Will shield for them. Oh, all that stuff. So there you go, 3d10.
Could you write 4s0?
You could put 4s0, okay? All right, so which species, zinc or zinc plus 2, has the greatest ionization energy? Oh, this is not redox, but it becomes redox. Well, zinc plus 2, or zinc. Now, what is ionization energy? It's the energy it takes to pull an electron away. And they could even ask you to write the reaction. And it would look like this. Zinc 0, or zinc, and you're going to what? Produce 2 electrons, and each one's negative. So you're going to produce 2 electrons, plus, and of course, you're going to produce zinc plus 2. And how are you going to do that? You're going to apply some energy. Okay, so the energy plus the zinc, and that would be an example of an ionization reaction. Now, who do you think is going to take more energy to pull electrons away? Who has the greatest? Zinc plus 2. So that would be, this one would be it. Now they want to justify your answer. Why would it take more energy? The electrons in zinc plus 2 are more stable because you are pulling electrons from what? Yes, the n equals 3, right? The electrons that came off first were what? 4. N equals 4 electrons. Aren't they physically farther away from the nucleus? N equals 4. So you would say, in many ways, say that the zinc plus 2, because the electrons have a what? Higher effective nuclear charge. Remember all that stuff? Now, there's many ways you could say that. I'm pulling electrons from the, what? N equals 3, but, or you could say by losing 2 electrons, electrons that are left have a higher effective nuclear charge, right? They feel the nucleus more. There's 2 electrons that are missing that were what? Probably shielding, definitely, okay? So an ion is always, a positive ion is always smaller because of the resulting electrons feel the nucleus more. So the effective nuclear charge increases. And that's just a little review, but you could have said it many ways. None of that is the redox yet, but those are the things that could pop up. Okay, who got oxidized? Now this is important. Who got oxidized? Now, the one thing you need to understand is one skill in redox is assigning oxidation numbers. Now it's kind of silly because they gave us 2 here. Looking back in the reaction, an elemental, okay, state of an atom is 0. Protons equal electrons. So the question is oxidation. If you forget, Leo the line says, losing electrons is oxidation. So who lost electrons and became positive? Remember, this is the answer. Remember, redox occurs here. This is the result. We would never pick any choices on this side. Someone gained and someone lost on the what? Reactant side. So if you have to write, okay, a half reaction, you'd see that aluminum 0 produces 3 negatives, and then it becomes aluminum plus 3. Okay, the charge increases going left to right as you lose electrons. So it's just some basic redox skills here. So who specifically lost? I'm picking from the product side, always. Okay, and by the way, what do metals love to do? Lose electrons. Metals oxidize. Okay, we don't pick from the product side. That'd be something that we would do even in Regents level. Okay, so we got past all of that. Okay, so obviously it's the aluminum. Now, we have the following. Now here comes the question. And in fact, there's actually no question. The diagram below shows a galvanic cell. Luigi Galvani, Alessandro Volta. These are the people that had an argument of what electricity was. Was it biologically inherent, or was it a process of the universe? Was it a rule of or some property of the universe? And of course, Alessandro Volta said that electricity is something that biology was using from the universe, or the ability of. Any case, both of them, they could say a galvanic cell or a voltaic cell. Now, if you notice something, if you look at the real question, there's a couple of things here that are not posted. Number one, in this question, which was 2010, okay, they gave you in your reference table a complete net potential table to look up if you need be. Okay? In the current test, they do not give you a net potential table. They give you the net potentials if the problem requires it. This problem does require it, so I put them there. All questions now, your reference table will not have a net potential. They'll put the parts of the net potentials, just like your homework this weekend, that last question, they gave you what you needed. Now, so that's why I put it there. Now, something else if you noticed in the question, which is page 2. And the reason I'm doing this, party people, is because I want you to understand that they did not give you a place to write half reactions. Did not write, and I know the overall ion reaction is posted there. There's a reason I'm putting it there, because it's an important skill that could help you. Maybe you're smart enough and you can do this without it, but I would suggest that you write your half reaction. So let's go to the first problem. And before we do so, let's review what this is. Okay? Now, based on the reaction above, they do say that, even in the real question, based on the reaction above, and knowing that aluminum is the one who oxidized, its charge went up. Okay? And so let's write that half reaction. I know they're not asking for this on the real AP. They could, but we're going to write it in so we can see what's going on. Aluminum 0 went to aluminum plus 3, and it gave off 3 electrons. That's the half reaction. What else happened? Well, zinc plus 2 gained 2 electrons. That's why electrons are on the reactant side, and became zinc 0. Now, of course, we're going to balance this here. Okay, notice we're absorbing 2 electrons and producing 3. So we want to balance the electrons. This could be part of a it could be another way they present this. So that's why I'm doing this, and you'll see my craziness. So I want a total of how many electrons? 6, common factor. So I multiply this by 2, and this becomes a 6. I multiply this by 3. 3 times 2 is 6, and this is 3. And you can see, party people, why the electrons will cancel. Okay, and of course, that gives me the exact overall. I know this is redundant. I know they gave you this. But sometimes it's very helpful to see what's going on here. And we'll see that in a second. So that's the overall. That's how they got that. Okay, now what else is happening here? We know aluminum is oxidizing. And a mnemonic you may have forgotten is anox, red cat. So we're going to annotate to this, even though they're not asking. Anox, and this is red cat. And what this tells me is that this side right here is the oxidation half cell. This is where oxidation occurs. In fact, aluminum 0 becomes aluminum plus 3. So a piece of solid aluminum became aqueous aluminum plus 3. This thing is getting smaller as it oxidizes, aluminum plus 3. I'm trying to awaken the gods here. You've known this before. So this, once it oxidizes, guess what? Is pushing charge, electrons, this way. From the what, people? From the anode always to the what? Cathode. Always. From the place that produces the electrons, that pushes them, to the place that receives them. So this is my anode, and it's pushing charge always in this direction. Now, who specifically is pulling the charge or accepting them? Now, if you said zinc, zinc is the cathode. It's the place of reduction, but specifically, it's the zinc plus 2 that's going to pull the charge. And so be careful with that question. Who specifically gets reduced? The cathode is the place of reduction, but in this case, okay, as in most, it's this ion that moves toward this negative now because electrons are building up, and the zinc plus 2, guess what? Becomes a solid. A0, solid, becomes ions over here, but zinc plus 2 becomes a solid, and this plates. This side's getting bigger. We're making a solid in the what? Reduction half cell. Red cat. So the reduction half cell. Okay. Now, battery's still dead because I haven't explained the salt bridge. Assuming the salt bridge wasn't in there, the salt bridge is required because what's happening as I make positive ions go this way, this is building up with positive charge, right? And over here, I'm losing zinc plus 2. I'm losing positive charge in my beaker. So what does the salt bridge do? Well, because of ions, and it allows only the ions. Remember, the electrons travel. What is the electrode? The electrode is the place of oxidation. It may or may not undergo oxidation. The cathode is the place of reduction. It may or may not go. In this system, this anode actually undergoes oxidation, but doesn't matter. These electrodes are the exact place where it happens. So, to make sure that this does not get buildup of positive, and to make sure that this doesn't lose its positive and become negative. Think about it. If this becomes negative by losing the zinc as we go this way, as it grabs electrons, electrons will never flow to a positive beaker. And electrons electrons wouldn't flow to a negative beaker, right? Because losing your zinc plus 2 means that this would become negative. This would become negative by losing my positive ions. And electrons wouldn't flow to that. By producing aluminum plus 3, electrons would never flow away from a positive, so therefore we need something to keep this from getting positive, from this being negative, and the salt bridge maintains electrical neutrality by allowing the ions to flow. And who's going to flow? The beaker to the left, the oxidation beaker, is getting positive. So who's going to flow? The negative ion is going to come down to try to eliminate the buildup of positive charge. And over here, the positive ion in the salt bridge is going to come down to replace the positive that was lost. And by the way, certainly you could say this positive ion may be able to what? Be attracted and move toward this way as well for the same reason. And look at here. This nitrate ion, negative, could also move up to fill this and do the same. So it allows only the ions to flow. And the job is to maintain electrical neutrality. Without the salt bridge, the battery is immediately dead. Okay? So that's just a little bit of review. And again, oh gosh, I remember all this now. Okay? So let's go on to the questions. The diagram includes a salt bridge that is filled with saturated solution of KNO3. That means it has the max amount of K plus and NO3 minus. Describe what happens as the salt bridge as the cell operates. We kind of covered that, but clearly what happens is the positive K plus is going to move toward the reduction half cell. So K plus ion moves toward the reduction cell of battery. To do what? To maintain electrical neutrality. What does the nitrate ion do? Moves toward the oxidation cell. Of battery or voltaic cell to maintain electrical neutrality. It allows ions to flow, but specifically the K plus. Sometimes we'll say draw the movement. Okay? Pretty simple stuff. Okay, E. They want the E0 cell. E0 cell, notice the little zero means a lot more to us now. This E0 is the total net voltage at standard conditions. Ooh, it's from a standard table, which means 25 degrees Celsius. And the concentrations are at what? Either 1 molar or 1 atmosphere pressure. Okay, it means more to us. These are standard conditions. And so we need net potentials. Now, in the original problem given, you had a reference table back when the course was a little bit different that you could look these up. In this current form, you'd have to go to the list. And they're always going to be written as reduction, which confuses people. The question is, one has to be flipped. But we learned that who is oxidizing? Aluminum, correct? So that one has to go in the reverse, which means the sign does what? Right. So if you have to, half reactions help. This becomes positive 1.66 volts. Why did I reverse the sign? Because this one's oxidizing. Just like your homework this weekend. That last question, they gave you all reduction. Somebody had to be flipped. Someone was oxidizing. Someone's charge, okay, was going up because you're losing electrons. Okay, so this one stays as put, the zinc plus 2, and that's going to be negative 0.76. So essentially, positive 1.76. So 1.66 minus, is it 0.77? Yeah, 76. So do your math. What do you get? 0.90? Boy, that's a point. Big deal. Now, one thing I will say, make sure you put the volts, make sure you have your sign is correct. Obviously, this positive is big enough to overcome this negative, right? Zinc is terrible. Zinc is terrible at reducing, but this pushing overcomes the lack of pulling by the zinc, okay? The bottom line is positive volts are given. Positive volts. Please put a unit. It may depend upon the entire question being right, so don't be lazy. All right? Now, one thing I will say as a reminder, do not take this voltage, and times it by 2, times it by 3. Do not do that. A voltage is nothing more than a potential difference of charge based upon the ability of that chemical to what? Push charge or get oxidized, based upon this chemical to pull charge and get reduced. It's an ability level. It's got nothing to do with how many are present. It's not a what? Rate of reaction. This is tied to spontaneity. We can have something that's spontaneous but not happening. We can have gasoline in a can, and it has oxygen next to it, but not reacting because of the activation barrier, right? So don't get thinking that I have to times this by 3. We're not talking about amperage. We're not talking about a flow of electrons. We're talking about an ability level. So that is independent of the electrons. Yes?
So we're never going to multiply by anything. We're just going to change the size.
That's right. That's something to always remember. We never multiply. You've been doing Hess law, and people think, and you've been dealing with KAs sometimes. If you put 2 KAs together, you can multiply the KAs. You can multiply the delta H's. But these are not being multiplied, just being added. Remember, delta H's depends upon energy per mole. Okay? This is just an ability level of the compound. And you don't change its ability by having more or less of them. You change the spontaneity of the reaction. We'll talk about that in a second. All right? That's an important point. We talked about it then, but I will remind yourself now because we've been doing that. So that's pretty simple. All right? Now, F, indicate where the value of the standard free energy change delta G for the cell is positive, negative, or 0. Now, back in September, we learned that positive volts equaled a spontaneous reaction. Spontaneous reaction. Okay? And I just told you that. If battery was positive, okay, it was spontaneous. Now, what do we know? A spontaneous process means that delta G, standard condition, is what? Negative. And you can memorize that, but now introducing for the first time, this is the last formula you actually use. And it's given to you in your reference table, okay? And let me show you what it looks like. Now, I'm showing you one of the older tables. A lot of this stuff is gone now, but what is here is this formula. If you look in your formula, and I'll write it here, delta G, this is the last, we're ready for it now. We weren't ready for it then because we didn't know what delta G is. Delta G, standard condition, is equal to N, fancy F, Faraday's constant, okay, times E0 of cell. Hey, first and foremost, there's a negative sign there. So if I've got positive volts from figuring out my net potentials, flipping the one that oxidizes, and what? Keeping the one that reduces, adding together. If we get positive volts altogether, Faraday's constant, if we remember, was a converting factor from total charge coulombs for 1 mole of electrons. How much charge? Okay, and notice this N here. Let's learn about this N. N is the moles of electrons that are balanced in the half reactions. Okay, so, and of course, if you've got positive volts, because of this negative sign, it's going to make what? Delta G negative. So there is the final link. Negative N, Faraday's constant, E of 0 cell. So this is brand new, but it's very simple. So let's go calculate it. All right. Where are we? So now, indicate, justify your answer. We did that fine. Now, let's calculate it also. Let's say they asked for the value. Now, let's go do that. So here we go. So delta G is equal to negative N, Faraday's constant, E0 of cell. I know they didn't ask for it. What I wrote here is good enough. But let's say they did, because in other places they will. Now the first thing is this. What is that N? Okay, so if I look at my half reactions, what is the number of electrons that are balanced in both sides? That's right. And if you didn't write half reactions, okay, you could clearly get this wrong. Maybe you couldn't figure it out, but given to this, you understand it has to be 6 electrons being absorbed in 6. So because there's 6 on both sides, that's the N. The N is the number of electrons in the half reactions on both sides. So we put that number there. So it's going to be -6. Now Faraday's constant, 96,500, what's the value? 40, let's look it up, I forget it, my gosh. All right, I should have memorized it this weekend, or I did, I forgot, it's been a while. So if we go to Faraday's constant, and I don't know if I have, oh yeah, it's 96,500. Okay, it's coulombs per mole. You don't have to memorize. It's given to you in your reference table. So let's put that in. And once we're done with this, I'll give you the break. Okay, so I got 96,500. And that is coulombs per what? Mole of electrons. It's an important conversion we're going to use. It converts my charge. Now, we're going to go to volts, and our volt was 0.90. And so now we put it together. All right? And it's going to give me, by the way, a volt in a coulomb actually will give me a joule there. It's a kind of a weird thing. I don't want to get crazy. So 0.9 times Faraday's constant, 96500, bless you, times -6. And so I get this crazy number, big number, -521. We'll just do that, and of course that equals, put that in what? If you're really cool, you know to put that in kilojoules. -521 kilojoules per mole. Okay, take your break. Okay, so little sidebar here, you don't have to know this, but a voltage, okay, is really and you don't have to know this, but is a joule of energy per coulomb of charge it pushes around. So the volts that we get in a battery from the pushing of the charge of the anode and the pulling at the cathode gives us the energy per charge of, so that when you take this, you notice something, the coulombs would what? Cancel, and you've got what? Joules per mole left over. And of course, one of the things they'll ask you most of the time to do is convert to kilojoules per mole, just because this is, by the way, very spontaneous, isn't it? Okay, which is what you want to have in a battery. You do not want to have equilibrium. Equilibrium in a battery means that what? Delta G is 0, voltage is 0. Okay, so that is all that's left there. So that's pretty straightforward. The only little tricky part is what this N is. This N was the balanced electrons in the half reactions. We're using Faraday's constant again, and we use the voltage. Okay, so very simple. So this is new. Delta G, standard, equals -N, fancy F, Faraday's E0 of cell. And this connects my positive volts, which will now become a negative delta G. It connects everything. It's the last thermodynamic quantity. I could not give this to you back in the beginning of the year because I didn't define delta G. I just said it was spontaneous. Okay? All right. So number G, a letter G. Okay? If the concentration of aluminum nitrate in the aluminum plus 3 half cell is lowered. By the way, the aluminum to aluminum plus 3 is the what? Oxidation. Right? So we're talking about the ratio of aluminum plus 3 to aluminum. So they're saying something here. They're saying if I increase aluminum nitrate, what is this delivering? Delivering what? Aluminum nitrate does what? Breaks apart into aluminum plus 3 and nitrate ions. Okay? So I'm increasing that. Okay, so I'm sorry, is lowered. So if I lower this from 1.0, now why was it at 1.0? Because we were finding standard conditions. E0 of cell is a thermodynamic quantity. Couldn't talk about it then, now we can. It makes more difference. So we're going from 1. Here's an AP question. What would be the molarity if I'm finding E0 cell of my ions? And they would have to be 1 mole, okay? So now I'm making this concentration smaller. Does the cell voltage increase, decrease, or remain the same? Well, now it's Le Chatelier's principle, right? Let's look at our reaction. Okay, overall reaction. You go to the top if you like, or we wrote it down here. So wait a minute. Where is this ion? You may think, oh, oxidation. It must be a reactant. Wrong. Aluminum plus 3 is a product. So, my party people, if I decrease this, and we're ready for this, right? Equilibrium, whatever it might be, is what? Products over what? Reactants, yes? Coefficients become exponents. Solids and liquids do not apply. I forgot the AL here. That's a solid. That's a solid. So really, what is this K? K is really the concentration of aluminum plus 3 squared over what? Zinc plus 2 cubed. And they certainly could ask for it, okay? But what do I know? If I decrease this, by the way, this is no longer K, it's a what? Q. K is whatever it is, okay? But so what I'm saying to you is if I make my Q smaller, hello, here's my YouTube, here's where K would be. Now we know that this battery is running, correct? It's spontaneous. So Q must be what? Less than K. So in some position, we have a spot here. Now, as the battery runs, it's dying. It's what? Eventually, Q will equal K and the battery's dead. All batteries will move in that direction. All spontaneous reactions will stop. Okay? So, by making Q smaller, I'm pushing this position. So the position was definitely here if it's running. So let's pretend it's here. And by doing what? Lowering aluminum plus 3, I'm now here. So the delta G of the forward reaction, okay, has increased on non-spontaneous conditions. Meaning we are more what? Spontaneous in the forward. Which means if I'm more spontaneous, the voltage has to do what? Why? Because negative N. N is staying the same. Faraday's constant staying the same. The voltage is going to increase. Okay? So how do you explain that? Well, I just kind of did in so many different ways. You could say, if I decrease a product due to Le Chatelier's principle, the forward reaction becomes more spontaneous. Or if you want to use your Regis level, if you lower aluminum plus 3, the reaction is going to shift to make more, shift toward the forward, which makes the forward reaction have positive volts. So the cell voltage, okay, will increase. And by the way, we answered this 1,000,000 times for every one I gave you. I did this 1,000,000 times, if you remember it. Okay, but we did it. Cell voltage increases because the forward reaction becomes what? More spontaneous. And why? You can be really, really cool here and say that what? The Q is now larger, much more larger than the K. Okay, and so all of that, I can say it so many different ways. But if you want to go Le Chatelier's principle, you can say by decreasing one of the products that was aqueous, remember you can't decrease the concentration of a solid, so by decreasing the aqueous product, the forward reaction became more spontaneous because it shifted to the right. So, and because you're making the forward reaction more spontaneous, the voltage increases. You could say by decreasing an aqueous product, you're making the Q value even more smaller, and therefore the forward reaction. Yes?
Yeah, you just wrote Q dot figure.
Oh my gosh.
Yeah.
Thank you. Sorry. I'm talking and I'm writing. I can't do many things at once. So thank you for stopping that. So the Q is that much smaller, sorry, than K. And so we know that we're at some position here. By decreasing a product, we're now going to be in this position. So now the Q is even greater than K and even more spontaneous. Okay, I'm not going to say anymore. We've been through these types of problems. So this reviews everything of a voltaic cell. explains why the salt bridge works, identifying a cathode and anode. What if they didn't give you this overall reaction? Okay, let's do that. What if they didn't give you the overall reaction? They were hinting from the reaction that this guy was oxidizing. They were giving that to you away. But they didn't have to. So if they didn't give you the overall reaction, you'd have to be armed with what? Just this. Christmas. Okay, let me get rid of this. And so, who is better at oxidizing? Remember, they're all written as reduction. The one who's better in going this way and have greater positive volts, okay, when it goes in the opposite, would be the aluminum. So that would tell you that this one, from the net potentials, is your anode. The first step in a voltaic cell, where is your anode? Okay? And it's usually the metal who is better at oxidizing will have more positive volts in the oxidation potential. Any questions? That's everything. That waking up a lot of things? Only thing new was the delta G thing. Okay, say bye to it. All right, so now let's go to, let's not get blank on this. Let's go to this guy. Now this is the second application of redox. This is electrolytic cell. Electrolytic cells, unlike a battery, a voltaic cell or galvanic, if you notice, requires a supply of energy because the voltage without the battery will be negative volts. This is a non-spontaneous process that needs to be driven with energy. We are carrying the pony up the hill, where the battery was, we were riding a pony. We were using the free energy. This must use free energy. The battery's creating free energy for us to use, whereas, or at least setting up a condition where we can utilize some free energy to run our phones and everything else. Here, we have to use free energy. Okay, so let's go mark this up. Even though they're not asking for the markup, let's just do that. Now, they're giving something away. In electrolysis, this is really electrolysis of a fused salt. There's also electroplating, yes? Oh, yeah.
Sorry.
No, sorry. I meant to give you the other one. I said to myself, I'll give it to him ready, and I forgot. Okay. So, now if you notice, in this packet, I also gave you what the question looks like, okay, from the AP Central. When you see a test, I added some things. Now, in electrolysis, normally we're making something happen that doesn't normally happen. So in this case, they're giving us a really important clue. We're making copper here, and then we have some bubblage. Okay, so if you read the question, external direct current power supply is connected to 2 platinum electrodes. It's platinum, could be graphite. These things are pretty inert, so they're not part of the redox, okay? Unlike the battery. It's immersed in a beaker with 1 molar copper sulfate at 25 degrees Celsius. Why 25 degrees Celsius? Standard temperature, so we can use what? E0. As the cell operates, copper metal is deposited on one electrode and oxygen is produced at the other. Okay, they gave you the 2 reduction potentials, always written that way. So we know we're making oxygen here. And it's bubbling because oxygen's an element at STP, or 25 degrees Celsius, the gas. So what do we know? We have copper plus 2 ions in here. And we know that it's becoming copper 0, screaming to us that this is happening here. Now, let's just look at this and see if we can identify what's going on. Is this reduction or oxidation where copper plus 2 becomes copper solid? Reduction. And what do we know the mnemonic? Red cat, right? So right away I know that this is the what electrode? It's the cathode. This must be the what? Anode. Now, they're not asking for this, but we should be able to understand what's going on here. Without these wires, these guys have nothing. Now, the anode is made because it's a place of oxidation. Okay? The cathode is here because of a place of reduction. Now notice something. What would make the copper plus 2 move in this direction? What charge? What charge do you think this has to be? Negative. Now, believe it or not, you're going to be happy about this. The AP doesn't ask for charges of electrodes. I made you learn them for understanding how this works. But, so you don't have to do this, but I know that this is negative. Here's how it makes me help you understand. How in the world did that cathode get negative? How does it build up a charge? What part of the battery may have delivered negative charge? The anode, right. So this part is the anode of the battery. And where does always charge always must flow? From, no matter what system I have. From the what? Anode to the cathode. And if this is the anode, it must be flowing what? Back to the cathode. Now, if you want to put the charges, because they make sense, the anode in the battery is always negative. The cathode of the battery is always positive. This negative makes this negative. This positive makes this positive. If you don't like the charges, it doesn't help you understand it, understand anode to cathode. But the important point is knowing that this was reduction. And red catting made this the cathode and the anode of the electrolytic cell. A cell that requires energy to force a reaction that normally would not occur. A non-spontaneous process. Okay, so that's the basics here. So now that we have all that down, let's look at the first question. We kind of delivered that. On the diagram, indicate the direction of electron flow in the wire. And we just did it. Okay, there's two wires, and you really should have written it like I did. From the anode to the cathode, and from the anode to the cathode. Did you need all of that? Maybe, maybe not. But I'm trying to make sure I awaken all the gods there. So I needed 2 arrows to show that. Okay? All right, so that's a point. Thank you very much. Write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. Okay, first and foremost, I know that I'm going to keep this one as is because that reduction is occurring. Okay? And we were making oxygen, correct? So this one is the what? Reverse. So this is the reverse, which means the charge becomes negative. Now if you notice, if you flip over to the question as presented to you by AP Central, they do not give you the oxidation half-reaction, the reduction half-reaction. I am suggesting to you that it is very helpful to do this because when I watch people do this, they get things wrong. They forget to balance something. So let's just rewrite it. Oxidation, okay? Clearly, the oxidation, I'm making O2 here. O2 is being produced. So clearly, this is the reverse reaction. So let's flip it. I'm making O2 plus 4 protons is being produced plus 4 electrons. Hey, electrons in the product side means I'm producing them. And guess who? 82 H2Os. And this charge, I'm just going to write it here, is negative 1.23. I flip the voltage. They're not going to do that for you. Now, I'm going to write this one as is. Copper plus 2 gains 2 electrons and becomes copper 0. Party people, the overall reaction must balance your charge. All you have to do is balance your electrons. And it's so easy to forget. I have so many students who are so smart, okay, that would put these two together and in the overall reaction show me 2 electrons being produced. You see how you could have done that? You've been balancing things in Hess's law. Hey, this has got 2, this has got 4, so you can put 2 electrons at the end because you've been doing it that way forever. But no. There's no electrons being shown. The amount of electrons that are being absorbed have to be produced, so what do I have to do to balance this? And that's something that a lot of people would miss. They have to times the bottom by 2. Balance the electrons. This becomes 4 and 2. And now, party people, I can balance these 4 electrons. By the way, this one stays as written, 0.34. Now I can write this. 2 copper plus 2 plus 2 waters that I had to flip around give me the oxygen, 4 protons, and there you go. Here's a point or 2, depending upon how they break it up. I forget. And yeah, I'll write it bigger. 2 coppers. Easy to get it wrong, as you can see. So don't do what I do. Do as I say. All right, so predict the algebraic sign of delta G. Well, this is electrolytic. It's non-spontaneous, and if you don't see it, party people, looky over here. What is this going to give me? A negative voltage. So because the E0 of cell is negative, it is non-spontaneous, which means delta G of 0 is positive. So you're predicting the delta G is positive because the E0 cell will be negative. Now you can use the actual real negative number. We're going to need that pretty soon. Okay? And so, my gosh, Oshkosh, pretty simple stuff here. Calculate it. All right? So delta G 0 is equal to negative N, fancy F, pinkies out, E0 of cell. So we're going to need E0 of cell. They're going to give you a point for doing E0 of cell. So that, if I remember, is negative 1.23.
Oh, it's random. Do they care how you write like the fancy app?
No, no, not at all. Point. Oh, it's 7, 9, 7, 8. So they'll give you a point for doing that math right there. Okay? As long as I did it right. So, what's negative N? It's going to be where? 4. The balanced half reaction, which they weren't asking you to do, really helps you get the N. Careful. Okay? So that's going to be 4, negative 4. Faraday's constant's 96,400. What number are they using now? 89? 85. Good. And that, of course, is coulombs per 1 mole of electrons. You don't have to put the units in, really. Negative 0.89 volts, which is really, you can just put volts in here. You don't have to put the units, but again, just as an aside, a voltage is the joule per charge that's pushed around, and that's why the coulombs cancel and you get joules per mole. And you put this in your handy-dandy calculator. And you're going to see that, guys, this is not hard.
Why don't you use moles for N? Is it just
Oh, no, N just means that balanced moles of electrons. Okay? In the half reaction. So negative 4 times 964, 5, oh, Christmas, 4. I always want to do the 500. 8, 5 times negative 0.89er. And I get 343. Now if you do this, you go joules per mole, you can lose a point here, party people, right? What's wrong with that? Yes, look, how many sig figs do I have?
a lot?
I have 2 here. This does not equate. This is a what? A standardized compound. That's a known thing that you didn't measure. It's a constant you didn't measure. We didn't measure this as well. So this was a value that was measured by some voltmeter. I have 2, so 3, 4. And normally they want this in kilojoules. I didn't ask for it, so I could either write 34000 or better yet 340 kilojoules per mole. And but don't forget that it is positive. Okay, that if you did all that work and this wound up being negative, you don't put that in, you're going to get that wrong. So careful, careful, careful. Not hard. Oh, we like electrochemistry? Yeah, you hated it in September, didn't you? This is nothing compared to what you've been doing. Okay? Now we're gonna awake some more gods. Now we have these last old problem. We've done this already. You forgot about this. But now I'm going to use amperage, which is not voltage. Amperage is actually the amount of charge from electrons that have been pushed or pulled by the voltage, the potential difference in the charge. So now, how much copper was made? So we have a voltage, okay, that's producing a current, a flow of electrons. Now think about this for a second. At the cathode, copper plus 2 is becoming pure copper. How did that happen? Copper plus 2 gained how many electrons? 2 electrons to become copper 0, which of course is a solid. So, if I can figure out how many electrons got to the cathode, I can assume that half that number gives me how much copper atoms are made, right? If I know total number of electrons that got to the cathode, okay, and I know that 2 electrons makes 1 copper plus 2 become copper, I can cut that in half to get total number of copper atoms. How do I do that? 2 ways. I have to use my amperage, okay? What is amperage? Okay, now amperage in your reference table is I, okay, and it's coulombs per second. In fact, if I have 1.50 amps, that means I have 1.5 coulombs of charge per second being passed around. Think with me for a second. If I know the coulombs or charge being passed around, and I know the total time, won't I figure out the total charge over that time period? And wait a minute. If I know Faraday's constant gives me what? The total charge per how many electrons, I can convert that to total electrons. And that'll give me half of that number, the copper being made. Moles of copper, convert that to grams, booyah. Let's go do that. We've done this already, but it's been a while, so let's go through it. So the first step is I take my 40 minutes. Convert to seconds. I know that 1 minute is 60 seconds. Booyah. Now why did I go to seconds? Because I know amperage is 1.50 is coulomb per second. So now, I'm going to convert this to the entire amount of coulombs. Using the what? Using my amperage. There is 1.5 coulombs of charge per 1 second. That's what the amperage means. This is not new, it's review. It's been a while. Okay, I get it. So what do we have so far? Seconds are gone. I have total amounts of charge that I got to the cathode. Now, I want to convert this charge to number of number of electrons. Faraday's constant. Now, Faraday's constant is coulombs per mole of electrons, but I'm going to get rid of coulombs. So 96.485. Okay. Coulombs per 1 mole of electrons. So now I've got total amount of electrons. Cool. But I want kappa. So what do? I know that there are 2 electrons that will make 1 copper. And notice here, what's left standing? Moles of copper. They said, what's the mass? Convert to moles. I see mole standing here. 1 mole is equal to 64 grams. That's the atomic mass. I don't think we have to go over that. And we are done. Now, in other parts of the course, I say get the math done. Forget about dimensional analysis. I really feel like this really helps you to do dimensional analysis, to feel like what you're doing. There's so many steps here. If you write this down 4 different times, there's really a chance of getting this wrong. I really feel like going across and this, it really is helpful to organize your thoughts. So 40 minutes times 60 for total seconds, times that by 1.5 for total coulombs, divide by Faraday's constant to get total amount of moles of electrons, 485. And then I divide by 2 because it takes 2 electrons to make 1. And of course I times that by 64. And I get, now, 1.19 grams. Why? This was measured. This was measured. I'm using 3. I think they use 1.2 in the key, but this is all good right here. And this is grams of copper. Remember that? Okay, that's been a while. Okay. F. All right, look at F. Redox question? What's F? I have temperature. How much O2 would I make? Listen, we just figured out how much what? Copper would produce. How much O2 gas? So what if I put a eudiometer tube, by water displacement, right? I filled up a tube of water, and I collected the bubbles. As the bubbles go up, it pushes the water out. And of course, let's assume no water, so it's dry volume. So I have temperature. I have the pressure. What's the liters? This is a what problem? Gas law problem. What? A gas law problem in a redox question? You betcha. So what we have? PV equals NIT. And we're going to solve for volume. So volume is equal to NIT over P. We have our temperature, which has to be converted to Kelvin. We're going to know our R, which is not in joules. We know the pressure. The question is, what is the moles? Now, how can I get the moles? Well, party people, look at the reaction. Now, this has nothing to do with redox other than, so what? Stoichiometry. Stoichiometry. What do we know? For every moles of what? Copper produced, there is what? Half. Hey, they love to sneak stoichiometry and what? Okay? These ratios with us. So, did they say the same time period? Yeah. So if I know the moles, which by the way, would be right here again. So here's my number of moles of copper. All I do is take this number, times it by 0.5, and I have what? Moles of what? My O2. So there's a little sneaky sneak there. But you just had to go back to the reaction. So you can see that this is redox, but party people, it's still everything mixed together. Okay, you've seen that before. So let's do it. I forgot, of course, divide by 2. I think I had 0.0187. 0.0187 if my calculator. I divided by 2. Yeah, that was my moles. So I'm going to take that and divide that by 2. Right? I think 0.0187 was my moles of copper. Is everyone right? And I divide that by 2 to get O2. Everyone see what I'm doing here? Okay, cool. Beans and chill. 0.0187 divide by 2. And so, setting this up, I get 0.00935 moles. My universal gas constant, not with joules. I need liters, atmospheres. It's been a while, but you have it in your reference point, 0.08206, something close to that. And that's liters, atmospheres, mole kelvins. This is all given to us. Temperature must be in Kelvin. We add 273 to the 25. It's been a while. 298 Kelvin. The pressure is 1.16. Now, putting the units in is really helpful, party people, especially for your gas law constant, because it tells us, number one, what units the other things have to be in. Atmospheres have to be this. We're solving for liters, and the temperature is in Kelvin, because all of that would what? Go bye-bye. Kelvin goes Kelvin. And so let's do this craziness. 0.00935. I had my calculator, but who cares? 0.08206 times 298 divide by 1.16. And if I didn't make any mistakes, which is at all possible, I get 0.197 liters. Now, 2 sig figs there. So I'm going to go 0.19, so 0.20 liters. Remember, this ending 0 counts. This would be a 2-pointer question. 1 point for recognizing the moles of the O2 is half that of the copper you just made, based upon the stoichiometric relationship, and then another point for probably calculating this through. And you can see this is what AP is about, putting it all together. All right? I am finished with the course. There is no more new information. That was all review, okay? So I am done today. I do have some work of home. Okay, and so I'll pass that out now. You can get started, and that's it.